What does it really mean to travel beyond the Milky Way, when even the edge of our own galaxy is not a wall, but a fading shoreline of stars, dark matter, and ancient motion? Tonight, on Calm Space Science, we begin a quiet journey outward from the soft glow of our galaxy, past its dwarf companions and the approaching Andromeda galaxy, toward the observable horizon, where the oldest light in the universe still whispers from the beginning of time. Along the way, we will meet pulsars, magnetars, distant quasars, small worlds around TRAPPIST-1, and the haunting silence behind the Fermi paradox. Before we begin, please take a moment to like this video, subscribe to Calm Space Science, and share it with someone who loves peaceful space stories. Thank you for spending your time here. What time is it where you are? And where are you watching or listening from? Tonight, leave a comment below. And now, let us gently step into the journey beyond the Milky Way. The Milky Way does not end at a line drawn through the dark. Its outer edge is not a bright rim, not a wall of stars, and not a clean border where one kind of space stops and another begins. It is more like a thinning, a gradual loosening of density, where the familiar disk of the galaxy fades into a wider halo of older stars, wandering clusters, invisible matter, and long streams left behind by smaller systems that came too close. From inside this structure, the boundary is especially difficult to picture. The sun is not looking at the Milky Way from the outside, as if the galaxy were a spiral painted on black glass. It is embedded within one of the galaxy's arms, carried around the center with gas clouds, dust lanes, young stars, ancien stars, and the quiet gravitational field that holds the whole system together. The view from Earth is therefore a view from within the pattern itself, and every attempt to understand the edge of the galaxy begins with that limitation. The Milky Way first appears as a pale band across the night sky because the eye is looking through the crowded plane of the disk, where countless unresolved stars blend into a soft river of light. That river is only the visible sign of something much larger. The galaxy is a vast rotating system made of stars, stellar remnants, gas, dust, planets, star clusters, and dark matter, all moving under the influence of gravity. Near the center, the density rises into a crowded bulge around the region of Sagittarius A, the supermassive black hole that anchors the innermost gravitational landscape. Around that central region spreads the disk, flattened and structured into spiral arms, where new stars continue to form inside cold clouds of gas. Farther out, the disk becomes thinner and less clearly ordered. But the galaxy does not simply stop. Its influence reaches outward through a halo that is harder to see and much harder to measure. This halo contains sparse old stars, globular clusters, and streams of material stretched out by gravity. It also contains the dark matter halo, a much larger and mostly invisible framework inferred from the motions of stars and gas. The dark matter cannot be seen directly with ordinary light, but its presence is written into the way the galaxy rotates. Stars far from the center move faster than visible matter alone would allow, and that mismatch tells astronomers that a hidden mass surrounds and permeates the luminous galaxy. Because of that hidden mass, the true boundary of the Milky Way depends on what is being measured. The bright stellar disk may span roughly 100,000 light-years, though even that figure softens at the edges. The faint halo reaches much farther. The dark matter halo may extend farther still, blending gradually into the gravitational territory of nearby galaxies. A galaxy, then, is not only what shines, it is also what shapes motion. This distinction matters because the outer Milky Way is a place where visibility and influence separate from each other. Stars become rare. Gas becomes patchy. Dust no longer forms the same dark lanes seen closer to the disk. Yet, gravity continues to work. And the galaxy keeps a kind of extended presence long after the main band of light has faded. In that region, the Milky Way is less like an island with a shore and more like a weather system whose pressure weakens slowly with distance. There are places where the pull of the galaxy still dominates, places where it competes with other pulls, and places where smaller galaxies are being drawn into its long history. The outer halo preserves evidence of those encounters. Some stars do not move as if they were born in the main disk. They follow elongated paths, gather into streams, or carry chemical signatures that point to different origins. These are not random details. They are fragments of a record. Over billions of years, the Milky Way has grown by absorbing smaller galaxies, pulling them apart as tides on Earth pull at oceans, but on a scale so wide that the process unfolds across ages almost impossible to feel. A dwarf galaxy approaches. Its stars are bound to it at first. Then the Milky Way's gravity begins to stretch the smaller system. The near side feels a stronger pull than the far side. Stars loosen. Gas is stripped away. The smaller galaxy becomes less like a separate body and more like a trail, a long arc of stellar debris, gradually wrapping around the larger system. The Sagittarius dwarf galaxy is one of the clearest examples of this continuing process. It has passed through the Milky Way's disk more than once, and its stars now form streams that trace the damage of those passages. What looks from a great distance like a single majestic spiral, in closer detail, a structure still being assembled. The galaxy carries scars and additions. Its outer regions are not empty outskirts. They are a memory field, where past mergers remain legible in motion. Even the spiral arms may have been affected by such encounters, stirred and reshaped by the passage of smaller companions. The Milky Way is therefore not a finished object. It is a continuing event, a slow gravitational composition still changing under the influence of what it has consumed and what still moves nearby. This makes the question of its boundary more subtle than a simple measurement. The edge of the bright disk is one answer. The edge of the stellar halo is another. The edge of the dark matter halo is another still. And beyond all of them lies the wider setting of the local group, where the Milky Way and its neighboring galaxies share a larger gravitational story. Before that wider region can be understood, though, the first step is to notice how uncertain the galaxy's own margin becomes. From the inside, the Milky Way feels like home because it contains the sun, the planets, and every familiar constellation. But as the journey moves outward, home begins to look less like a central place and more like one small location inside a layered structure. The spiral arms are not fixed material arms like the spokes of a wheel. They are regions where stars and gas gather more densely, where waves of compression help produce new stars, and where bright young objects make the pattern visible. The sun moves through the galaxy on its own long orbit, taking hundreds of millions of years to circle the center once. During that movement, the local sky changes by degrees, far too slow for human senses. Stars that seem permanent drift. Clouds disperse. Clusters dissolve. The galaxy turns, but not as a solid object. Inner regions orbit faster than outer regions, and the whole system is shaped by a balance of motion and gravity. At the outskirts, that balance becomes especially revealing. If the visible matter were all that existed, stars at large distances should move differently. They should betray a weaker hold from the galaxy. Instead, their motion points toward additional mass, unseen but influential. This is one reason the outer Milky Way is scientifically important. It is not only the place where the galaxy fades, it is the place where the hidden structure becomes impossible to ignore. The same faint outskirts that seem visually quiet carry some of the strongest clues about what the galaxy is made of. There, astronomy becomes a study of traces rather than spectacle. A sparse star with an unusual path, a globular cluster far from the disk, a stream curving through the halo, or a faint dwarf companion half hidden by dust may reveal more about the galaxy's growth than a bright region crowded with new stars. The boundary is therefore not silent. It speaks in weak signals, in patient measurements, in motions, gathered over years by careful surveys of the sky. The difficulty is that the Milky Way's own dust often blocks the view. Some nearby dwarf galaxies are hard to detect, not because they are truly remote, but because they lie behind the crowded and obscuring plane of the galaxy. The very structure being studied interferes with the act of seeing it. For a long time, this meant that the nearest companions could remain unnoticed, hidden by foreground stars and dark patches of interstellar material. As instruments improved, the population of known satellite galaxies grew, and with each discovery, the Milky Way became less solitary. It became the central member of a small swarm, surrounded by companions of different sizes and histories, some intact, some distorted, some already dissolving. These satellites make the idea of a galactic boundary even softer. A dwarf galaxy orbiting the Milky Way is beyond the bright disk, yet not beyond the Milky Way's influence. A stream of stars pulled from such a companion may cross the halo like a loose thread, belonging partly to the lost dwarf system and partly to the larger galaxy that is absorbing it. In this region, identity itself becomes gradual. The outer Milky Way is made of material born in place and material acquired from elsewhere, and over enough time, the distinction blurs. This is how galaxies grow without ceremony. They do not need to collide in a single, visible instant. They gather, stretch, disturb, and absorb. They reshape one another through repeated passages. They leave behind arcs, shells, and streams. The calm appearance of the night sky hides that history because the motions are slow and the distances immense. But slowness is not stillness. The outer Milky Way is active in the language of deep time, and its edge is a living record of that activity. To journey beyond the Milky Way, then, is not to pass through a gate. It is to move through a long transition from the dense star fields of the disk into the thinner halo, from visible structure into hidden gravity, from the familiar river of light into a region where neighboring galaxies begin to matter. The first boundary is not a wall, but a question: where does the galaxy stop being a place and become an influence? That question cannot be answered by brightness alone. It has to be answered by motion, by mass, by the history of smaller systems falling inward, and by the faint stellar remains left behind. At the shoreline of the Milky Way, the galaxy is already becoming something larger than itself, because every edge points toward another gravitational relationship waiting beyond it. The faint companions of the Milky Way do not announce themselves like grand spiral galaxies. Many are dim, irregular, partly hidden by foreground stars, and easily mistaken for loose stellar excesses rather than separate systems. Yet these small galaxies are among the most revealing objects around the Milky Way, because they show that the galaxy is not only surrounded by empty space, it is surrounded by unfinished relationships. A dwarf galaxy can orbit for billions of years, slowly losing stars, gas, and shape, until its original form becomes difficult to recover. It may begin as a small gravitational island, with its own clusters and old stellar populations. But repeated passages near the Milky Way turn it into something stretched and vulnerable. The Sagittarius dwarf galaxy carries this story with unusual clarity. It lies close enough to be deeply affected by the Milky Way, and its long tidal streams show that it has already been pulled apart across a great arc of the sky. The word tidal is useful here because the process is related to the same principle that raises tides on Earth, though the scale is far larger and the material being lifted is not water but stars. The nearer side of the dwarf galaxy feels a stronger gravitational pull than the farther side. Over time, that difference loosens stars from the smaller system. Some drift ahead in the orbit, others trail behind. A once compact galaxy becomes a ribbon, and the ribbon becomes part of the Milky Way's halo. What remains is not only destruction, it is also growth. The larger galaxy gains material, the halo gains structure, and astronomers gain a record of the encounter. Sagittarius is not merely falling inward in a simple straight line. It follows an orbit that has carried it through or near the Milky Way's disk more than once, and each passage has left consequences. Some models suggest that these repeated crossings may have helped stir the Milky Way's disk, influencing waves, ripples, or even aspects of its spiral pattern. That possibility is important because it changes the role of dwarf galaxies. They are not just small objects being consumed. They can also be agents of disturbance, able to alter the larger system that appears to dominate them. The Milky Way may be massive, but it is not immune to touch. Its disk can bend, its stars can be lifted into waves. Its outer regions can respond to a passing companion, like the surface of a pond responding to a slow, heavy movement beneath it. This does not mean every feature of the Milky Way comes from Sagittarius, or that the story is simple. Galactic disks are shaped by many processes at once, including internal rotation, gas flows, star formation, and the wider pull of dark matter. But the presence of Sagittarius makes one fact difficult to avoid. The Milky Way's present form includes the memory of smaller galaxies. In the calm language of deep time, even a dwarf system can leave a handwriting across a giant. The Magellanic Clouds offer a different kind of companionship, unlike Sagittarius. The large and small Magellanic Clouds are still visually distinct dwarf galaxies, bright enough from the southern hemisphere to have been known long before modern telescopes could resolve their deeper structure. They appear as pale patches of light, detached from the main band of the Milky Way, yet gravitationally connected to it. The large Magellanic Cloud is the larger of the pair. A dwarf galaxy rich in gas, active star-forming regions, and massive young stars. It contains the Tarantula Nebula, one of the most intense nearby nurseries of massive stars, where gas is compressed, illuminated, and sculpted by the radiation of new stellar generations. The small Magellanic Cloud is more modest, more irregular, and also deeply shaped by interaction. Between and around them stretches a great stream of hydrogen gas, a sign that gravity has been pulling material loose as the clouds interact with each other and with the Milky Way. These streams are difficult to sense in ordinary, visible light, but radio observations reveal them as extended structures, quiet and immense, showing that galactic interaction does not require a collision of stars. Gas can be drawn out first. Orbits can shift. Shapes can distort. Star formation can be encouraged in some places and suppressed in others. A companion galaxy becomes a reservoir, a disturbance, and a future addition all at once. The Large Magellanic Cloud is especially important because it is massive enough to influence the Milky Way more strongly than many small satellites. Its motion suggests that it may not have been orbiting quietly around the Milky Way for all cosmic time. It may be on an early passage, or at least on a path more recent and dynamic than older assumptions allowed. If that is true, then the Milky Way is not simply the settled center of a long-established system. It is responding now to a significant visitor, a companion large enough to tug on the halo, affect satellite orbits, and perhaps shift the position of the Milky Way's own disk relative to its extended dark matter surroundings. The idea is subtle but powerful. The galaxy that seems to contain the local night sky may itself be slightly displaced, slightly pulled, slightly unsettled by the arrival of a neighboring dwarf. The calm view from Earth hides this movement because there is no sudden visual event. There is only motion accumulated over millions and billions of years. The Magellanic Clouds also remind astronomy that dwarf galaxies are not all simple leftovers. Some are chemically rich. Some continue forming stars. Some have histories of interaction with each other before their relationship with the Milky Way becomes dominant. The Small Magellanic Cloud and the Large Magellanic Cloud are linked not only by proximity, but by a shared gravitational past. And their mutual disturbance has helped create bridges and streams of gas. In this way, the outskirts of the Milky Way are not a single hierarchy with one large galaxy and many passive fragments. They are more like a small environment of moving bodies, each with its own history, each altered by the others. Dwarf galaxies may look faint because they contain fewer stars, but they carry some of the most important evidence about how galaxies build themselves. Their stars are often old. Their dark matter content can be high compared with their visible matter. Their chemical abundances can preserve earlier stages of cosmic enrichment, before many generations of stars had filled the gas with heavier elements. When one of these galaxies is torn apart, that evidence is not always erased. It becomes distributed through the halo, where stellar motions and chemical patterns can still reveal that the stars were born elsewhere. This is one reason modern surveys of the Milky Way search not only for bright objects but for patterns in position, velocity, and composition. A star in the halo can be a clue. A group of stars moving together can be a fossil stream. A faint overdensity can mark the surviving core of a companion. Slowly, these clues change the image of the Milky Way from a single isolated spiral into a layered structure assembled through many acts of capture. The process is still occurring. Some satellites remain intact enough to be named as galaxies. Others are already dissolving. Others may be so faint that they are only now becoming visible in large sky surveys. Each one adds a small correction to the map. The nearest universe, then, is not empty and not still. It is populated by dim companions whose importance is larger than their brightness suggests. The Milky Way gathers them without hurry, and their response is written across the halo in streams. Warped gas, scattered clusters, and altered motion. There is a quiet sadness in this, but not in a human sense. The smaller systems lose their borders. Their stars are redistributed into a larger body. Their separate identity thins until only motion and chemistry remember where they came from. Yet that same loss is part of how large galaxies become what they are. The Milky Way's beauty is not separate from this history of accretion. Its halo is partly made of former companions. Its outer structure may carry the effects of their passages. Its future mass will include more of what is now still outside it. Beyond the bright disk, the galaxy is not ending. It is digesting its surroundings, slowly and imperfectly, while the companions around it trace the next stages of that transformation. Sagittarius shows the advanced stage, already stretched into streams. The Magellanic Clouds show the living stage, still bright, still gaseous, still forming stars, but already bound into a wider fate. Together, they make the same lesson visible from two distances in time. The Milky Way is not alone beyond its edge. It is accompanied by smaller worlds of stars, and those companions are helping write the future shape of the galaxy that holds the Sun. Beyond the torn streams and dwarf companions of the Milky Way, the next structure is not a single object, but a shared gravitational neighborhood. It is called the local group, and its quietness can be misleading. From Earth, the galaxies within it seem fixed in separate directions on the sky, like small islands of light set into darkness. In reality, they form a loose, moving association spread across millions of light years, bound not by rigid structure, but by mutual attraction. The Milky Way is one of its largest members. Andromeda is another. Triangulum, smaller but still substantial, belongs to the same family. Around them move dozens of dwarf galaxies, some attached to the larger spirals, some drifting through the group in more independent paths, some so faint that their discovery depends on patient surveys and careful separation from foreground stars. The local group is therefore not a cluster in the grandest sense. It is not like the dense galaxy clusters where hundreds or thousands of galaxies gather in a deep shared potential well. It is more modest, more open, and more intimate in cosmic terms. A small congregation of galaxies held together against the general expansion of the universe. That last point matters. On the largest scales, galaxies tend to recede from one another as space itself expands. But within gravitationally bound systems, local attraction can overcome that expansion. The Milky Way and Andromeda do not simply drift apart with the stretching universe. They are moving toward one another, because their mutual gravity dominates over the cosmic expansion between them. The local group is one of the places where the universe's broad outward tendency gives way to a smaller inward story. It is a region where galaxies are still turning around one another, falling together, and reshaping their shared future. The motion is slow only by human standards. In galactic time, it is consequential. A galaxy's path through the local group can decide whether it remains separate, becomes a satellite, loses gas, forms new stars, or is eventually absorbed into a larger system. The dwarfs closest to the Milky Way and Andromeda reveal the smaller version of this process, but the whole group carries the same principle at a wider scale. Gravity is arranging the neighborhood, not as a completed design, but as a long negotiation between mass, motion, and time. The local group has a rough center of mass, and the major galaxies move around that invisible balance. The Milky Way and Andromeda dominate much of the group's weight, while Triangulum may be bound to Andromeda or moving in a close relationship with it. Around these large systems, dwarf galaxies trace different histories. Some are gas-poor and quiet, their star formation largely ended. Others still contain gas and may continue to form stars under the right conditions. Their differences are not accidental. A small galaxy is more vulnerable than a large one. Its gravity is weaker, so gas can be stripped away more easily by tides, by pressure from surrounding material, or by bursts of star formation that drive gas outward. Once the gas is lost, the galaxy can no longer make many new stars, and it fades into an older, dimmer system. In that way, location becomes destiny. A dwarf galaxy that spends time near a giant may be transformed by the encounter, while one farther out may preserve more of its original material. The local group is full of such quiet contrasts. It contains active spirals, faint spheroidals, irregular dwarfs, star-forming clouds, old clusters, and streams that show where objects have already begun to dissolve. The larger pattern is not a static map, but a record of environmental pressure. Every galaxy in the group carries some evidence of where it has been and what has acted upon it. the Magellanic Clouds, still rich in gas, suggest recent and ongoing interaction. Sagittarius, stretched and disrupted, shows a deeper stage of capture. Dwarf spheroidal galaxies near the Milky Way, with little gas and mostly older stars, show what can remain after a small system has been stripped and quieted. Around Andromeda, the same kind of evidence appears in satellite galaxies and stellar streams, revealing that it too has grown through accretion. The Milky Way is not unusual in this respect. Large galaxies commonly build themselves by gathering smaller ones. What makes the local group valuable is that it is near enough for this process to be studied in fine detail. In distant galaxies, similar events may appear as faint shells, distorted shapes, or unresolved streams. In the local group, individual stars can sometimes be measured, their motions tracked, their chemistry compared. This transforms the region into a kind of nearby laboratory for galactic history. The evidence is not dramatic in the ordinary sense. It comes from positions on the sky, velocities along a line of sight, proper motions measured with great care, and the chemical fingerprints left by earlier generations of stars. Yet from these quiet details, a large story emerges. The local group has not always looked as it does now. Its galaxies, formed from early concentrations of matter, grew by merging and accretion, and gradually sorted into the arrangement visible today. Some members have been lost into larger halos. Some are in the process of being lost. Others remain distant enough that their future is less immediate. Above all of them lies the influence of dark matter, the unseen mass that helps bind galaxies and groups together. Without dark matter, the motions within galaxies already become difficult to explain. At the local group scale, the same hidden component helps shape the gravitational landscape in which galaxies move. The visible galaxies are therefore only the luminous peaks of a larger mass distribution. They show where stars have gathered, but not the full extent of what guides their paths. This is one reason the local group feels both knowable and unfinished. It is close enough that many of its members can be catalogued, yet its deepest structure still depends on matter that cannot be directly seen. The group also exists within a larger setting. It lies on the outskirts of the Virgo supercluster and within an even broader arrangement of cosmic filaments and voids, where galaxies are not distributed evenly but gathered along immense strands. The local group is small compared with those structures, but it participates in their motion. It moves relative to nearby clusters, responds to larger concentrations of mass, and occupies one modest region of a vast cosmic web. This wider context softens the meaning of beyond. Leaving the Milky Way does not mean entering empty, unrelated space. It means passing from one gravitational scale to another. First, there is the galaxy, with its disk and halo. Then there are the satellites and streams around it. Then comes the local group, where several galaxies share a long-term fate. Beyond that are groups, clusters, superclusters, filaments, and voids. Each scale has its own kind of structure, and each one changes the meaning of distance. 1,000,000 light-years feels enormous beside the size of the Milky Way's disk. Yet within the local group, it is part of the neighborhood. Several million light-years seems wide enough to isolate galaxies forever. Yet gravity can still bring the major members together over time. This is one of the calm reversals of cosmic geography. Distance does not always mean separation. Sometimes it only means a longer fall. The Milky Way and Andromeda are the clearest example. But even before their future meeting, the local group is already connected through motion. The galaxies are not suspended ornaments. They are bodies with trajectories, histories, and changing relationships. Their present arrangement is only one frame in a long sequence, far in the past. The early local group would have contained smaller building blocks, gas clouds, and young galaxies still assembling. In the present, the large spirals dominate the region, surrounded by companions and debris. In the future, the same group will likely become simpler in appearance as major mergers combine what are now distinct systems. The number of visible separate galaxies may shrink, even as the total mass remains. This is how cosmic structure can become both larger and less varied at the same time. Mergers build mass, but erase some separateness. They create new halos, redistribute stars, and transform spirals into broader, more elliptical forms. The local group is therefore a temporary arrangement, not because it is brief, but because nothing in it is beyond change. Its drift is slow enough to seem peaceful and strong enough to decide the future. From the perspective of a quiet journey beyond the Milky Way, this region is the first great widening of context. The galaxy of the Sun becomes one member among others. Its companions become part of a wider population. Its edge becomes only an inner boundary inside a larger gravitational field. The familiar night sky, with its stars belonging almost entirely to the Milky Way, gives little hint of this surrounding architecture. Only a few neighboring galaxies can be seen without instruments, and even they appear faint, small, and still. But their stillness is an illusion created by distance and time. The local group is moving. It is folding inward in places, stretching in others, and carrying the evidence of past encounters in the faint light of its outskirts. It offers a gentle but profound correction to the idea of isolation. Beyond the Milky Way lies not an immediate emptiness, but a family of galaxies, some bright, some nearly invisible, all participating in a shared and unfinished drift. Andromeda approaches without appearing to move. On clear nights, far from artificial light, it can look like a pale smudge in the northern sky, soft enough to be mistaken for a small cloud and steady enough to seem almost outside time. Yet that faint oval is a galaxy larger than the Milky Way in visible extent, filled with hundreds of billions of stars, dark lanes of dust, clusters, gas, stellar remnants, and its own company of satellites. Its quiet appearance is a result of distance, not stillness. Andromeda is moving toward the Milky Way, and the two great spirals of the local group are bound into a future that neither will avoid. The distance between them is usually given as about 2.5 million light-years, a span so wide that light itself needs longer than the whole history of human ancestry to cross it. But within the scale of galaxies, that distance is not an impossible separation. It is a wide interval inside a shared gravitational field. Andromeda and the Milky Way are not strangers passing in unrelated directions. They are the two dominant masses of their neighborhood, and their mutual attraction has been shaping the local group for billions of years. The evidence for Andromeda's approach comes from its light. Like many astronomical measurements, the discovery is not made by watching a visible object slide across the sky from one human lifetime to another. It comes from the slight shift in wavelength that reveals motion along the line of sight. Andromeda's light is blue shifted, meaning its wavelengths are compressed as the galaxy moves closer. This does not mean every part of its motion is aimed perfectly at the Milky Way, because galaxies also have sideways movement, and that transverse motion is harder to measure. But careful observations show that the future encounter is not merely possible, it is expected. The timescale is measured in billions of years, with the first major passage likely far beyond the lifespan of the present human world, but not beyond the lifespan of the galaxies themselves. The coming merger is often imagined as a collision, though that word can mislead. Galaxies are mostly empty space. Even in the crowded disk of a spiral, the distances between stars are enormous compared with the sizes of the stars themselves. When Andromeda and the Milky Way begin to interpenetrate, the chance of two individual stars striking each other directly is extremely small. The more important collision is gravitational. Each galaxy will pull on the other. Their disks will distort. Long tidal tails may stretch outward. Star streams will form. Gas clouds may be compressed, triggering new star formation in some regions. Orbits that once seemed settled will be rearranged into a broader and more turbulent structure. The encounter will not be a single moment, but a sequence. The galaxies will pass through or around each other, separate, slow, turn, and fall together again, losing orbital energy through gravitational interactions until they finally settle into a merged remnant over immense time. The elegant spiral shapes may fade into a larger elliptical or lenticular galaxy, a smoother system containing the redistributed stars of both ancestors. The future object is sometimes informally imagined as a combined Milky Way and Andromeda galaxy, but any name matters less than the transformation itself. Two grand spirals will become one larger structure, and the local group will be changed at its center. The Sun, if it still exists as a recognizable star at that time, will not experience the merger as a sky filled with crashing suns. Its orbit around the galactic center may be altered. It could be carried into a different region of the new galaxy, perhaps farther from the merged core. The night sky, from any surviving world, would change gradually across ages. Andromeda would grow larger, its disk becoming more detailed, its dust lanes more pronounced, until the two galaxies no longer looked like separate forms. But this would happen slowly, with a patience that belongs to gravity rather than to human drama. The approach of Andromeda also casts the present Milky Way in a different light. It shows that even a galaxy as vast and familiar as the one containing the Sun is not a final frame. It is a temporary arrangement in a longer sequence of assembly. The Milky Way has already absorbed smaller galaxies and continues to gather companions. Andromeda has done the same. Its halo contains streams and substructures that point to earlier mergers, including encounters with smaller galaxies that were stretched and consumed. Both spirals are therefore products of older accretions, and their future meeting is not an exception to cosmic history. It is the same process at a larger scale. The local group is moving towards simplification through merger, just as smaller systems have already been simplified into the halos of larger ones. This does not make the galaxies less beautiful. It makes their beauty less static. Their spiral arms, star-forming regions, and satellite systems are all passing forms, maintained for long intervals but never guaranteed forever. Andromeda's approach is a reminder that structure in the universe can be both stable and temporary, enduring for billions of years while still moving toward change. There is another quiet detail in this future. The Triangulum galaxy may also participate in the encounter, either as a companion affected by Andromeda's motion or as a later participant in the merged system. Its role is less visually famous, but it belongs to the same gravitational story. Around all three galaxies, satellite systems will be rearranged. Some dwarfs may be thrown into new orbits. Others may be absorbed. Stellar streams will lengthen and fade. Dark matter halos will overlap and combine. The visible merger will be only the shining part of a much larger invisible interaction. Long before the stellar disks fully blend, the dark matter halos of the Milky Way and Andromeda may already extend far enough to sense each other as parts of one approaching structure. This hidden overlap is difficult to picture because dark matter does not shine. yet it shapes the entire event. The galaxies are not only disks of stars on a collision course. They are luminous centers embedded in vast halos of unseen mass. And those halos guide the way the encounter unfolds. The first contact, in a gravitational sense, is therefore not the meeting of star clouds, but the deepening of a shared field. As the two galaxies draw closer, the distinction between their territories will weaken. The question of where one ends and the other begins, already soft in the outskirts of any galaxy, will become even softer. In the end, the merger will erase not the stars, but the old boundaries around them. Andromeda also changes the emotional scale of the journey beyond the Milky Way. It is far enough away to be another galaxy entirely, yet near enough to be part of the same future. It is not an unreachable abstraction at the edge of the observable universe. It is a neighboring spiral whose light has crossed intergalactic space and entered human eyes. That light began its journey before modern humanity existed, before cities, before agriculture, before any written sky map. When it arrives, it carries a view of Andromeda as it was in the distant past, while the galaxy itself has continued moving closer during the light's travel. Every observation of Andromeda is therefore layered. It is present in the sky, past in its light, and future in its motion. This triple nature gives it a special place in the local group. It is an object that can be seen directly, measured scientifically, and placed into a forecast so vast that it exceeds nearly every ordinary sense of time. The approach is not threatening in any immediate way. It is too slow for urgency, but it is not meaningless because of that slowness. The longest processes often do the most shaping. Mountains rise slowly. Continents drift slowly. Stars age slowly. Galaxies merge slowly. Andromeda is part of that family of changes whose power lies not in suddenness, but in persistence. The faint patch in the sky is the visible face of a gravitational decision already in motion. Nothing about it needs to be rushed to be profound. As the journey moves outward, Andromeda becomes the first major reminder that beyond the Milky Way, there are other great structures with their own histories, their own satellites, their own scars, and their own futures intertwined with ours. It stands as both neighbor and destination, both ancient light and approaching mass. The Milky Way's edge led into companions. The companions led into the local group, and the local group now gathers around the slow meeting of its two largest spirals, a meeting that will one day redraw the central map of this small cosmic neighborhood without ever needing to announce itself as a catastrophe. The observable horizon is not the place where the universe ends. It is the place where information, carried by light, has had only a limited time to reach any observer inside cosmic history. That distinction is quiet, but it changes everything about the journey outward. A horizon on Earth can look like a boundary because the ground and sky seem to meet there. Yet walking toward it only moves the apparent edge farther away. The cosmic horizon is stranger, because it is not produced by the curve of a planet beneath the feet, but by the age of the universe, the finite speed of light, and the continuing expansion of space itself. Every telescope looks backward as well as outward. The light from the moon is already old by the time it arrives. The light from the sun is older still. The light from Andromeda has crossed intergalactic space for millions of years. Beyond those familiar distances, the delay becomes so great that looking far enough away becomes a way of seeing the universe when it was younger, denser, and less fully assembled. The observable universe is the region from which light has had time to arrive since the hot early state from which the modern cosmos expanded. Its radius is often described as about 46 billion light-years, not because the universe is only that old in ordinary travel time, but because space has expanded while the light was moving. The oldest light did not cross a static emptiness. It moved through a universe that was stretching. So the regions that emitted it are now much farther away than a simple multiplication of light speed by age would suggest. This is one of the first difficult ideas beyond the Milky Way and its neighbors. Distance in cosmology is not a single plane measurement. There is the time light has traveled. There is the present distance to the region that sent it. There is the redshift, the stretching of its wavelength as space expands. There is the distance that depends on how brightness appears, and another that depends on apparent size. These measurements are related, but they are not identical, because the universe itself is dynamic. A galaxy whose light has traveled for more than 13 billion years can now be tens of billions of light years away. Nothing has broken the rule that matter cannot move through local space faster than light. Instead, the space between distant galaxies has grown. The expansion is not an explosion from a central point into a surrounding emptiness. It is a change in the scale of space everywhere, a widening of distances between regions that are not gravitationally bound to each other. Inside the Milky Way, gravity holds stars together. Inside the local group, gravity binds the major galaxies strongly enough that Andromeda approaches rather than recedes. But across larger cosmic distances, the expansion becomes the dominant pattern. Galaxies that are far enough away appear to move from us not because they are racing through space in the ordinary sense, but because the space between the regions is increasing. Their light stretches on its way, shifting toward longer, redder wavelengths, and the amount of that stretching becomes one of the main ways astronomers infer distance and cosmic history. The observable horizon is made from this combination of age and expansion. It is a limit to what can be seen now, not necessarily a limit to what exists. Beyond it may be more universe, perhaps much more, perhaps arranged with the same broad laws and matter, but lying outside the region from which light has yet reached us. The phrase, beyond the observable universe, can invite images of a wall, a border, or a dark outer country. The science points towards something less dramatic and more subtle. It suggests an unseen continuation, separated not by a physical barrier, but by causality. If a signal has not had enough time to arrive, it cannot enter the present map. If expansion carries regions away fast enough, some signals emitted now may never arrive at all. This produces a universe where the visible part is not the whole, and where the whole may be permanently larger than any possible observation. The horizon is therefore both a boundary and not a boundary. It bounds knowledge, not necessarily existence. It marks what can be connected to the observer by light, not what reality must contain. This is why the journey outward becomes less like travel through a landscape and more like entry into the limits of evidence. Nearby space can be mapped by parallax, by motion, by individual stars, by the structure of galaxies. Farther out, galaxies become faint smudges, then small red points, then difficult signals pulled from deep surveys. At greater distances still, individual galaxies give way to the early glow that fills the sky in every direction, the cosmic microwave background. Before reaching that ancient light, the universe already changes character. It is no longer filled with mature galaxies like the Milky Way or Andromeda. The earliest galaxies are smaller, more irregular, and often rich with young stars. Their light is stretched by expansion until it slips into infrared wavelengths, which is why modern observatories designed for infrared vision are so important for studying the deep past. Each high redshift galaxy is not merely far away. It is a record from a time when cosmic structure was still assembling, when stars were beginning to enrich space with heavier elements, and when black holes and young galaxies were already growing in ways that sometimes challenge simple expectations. The farther the observation reaches, the more it becomes a study of formation rather than finished form. Spiral arms, settled disks, and calm galactic halos become less common. Clumps, mergers, bursts of star formation, and compact luminous sources become more important. The universe seen near the horizon is not just the present universe placed at a great distance. It is the universe at an earlier stage of its life. That is why the observable horizon carries a double meaning. It is far away in space and deep in time. To look toward it is to look into conditions that no longer exist in the same form nearby. Yet even this deep view is shaped by selection. The most distant objects detected are often the brightest, the most strongly magnified by intervening gravity, or the ones whose light happens to fall into wavelengths that instruments can capture. The map near the horizon is therefore incomplete in a different way than the map nearby. It is not only limited by distance, but by the sensitivity of instruments, the opacity of intervening matter, and the difficulty of interpreting weak signals from a young universe. Cosmic expansion adds another quiet complication. There are galaxies visible now whose future light, emitted in the present cosmic age, may never reach the Milky Way. As expansion accelerates under the influence of dark energy, distant regions can cross beyond an event horizon of communication. Their old light is still arriving, showing them as they were long ago, but the possibility of receiving new information from them gradually closes. In the far future, if acceleration continues, galaxies beyond the gravitationally bound local region will recede from view. The local group, or the merged remnant it becomes, may remain visible to its own inhabitants, while the wider universe fades into darkness beyond reach. This does not mean distant galaxies vanish all at once. Their signals weaken, redden, and arrive more sparsely, until practical observation becomes impossible. The present era is therefore unusually rich. The sky still contains evidence of nearby galaxies, distant clusters, young galaxies, and the early glow beyond them. The universe has not always been so transparent to its history, and it may not remain so revealing forever. This gives the observable horizon a kind of scientific tenderness. It is not merely a limit that frustrates knowledge. It is also a temporary gift, a boundary currently bright enough to teach. From within the Milky Way, the edge of the galaxy felt soft because matter thinned and gravity extended outward. At the scale of the observable universe, the edge is soft in a different way. It is made of time, expansion, and the speed at which information can travel. There may be no physical surface there, no final shell of stars, no outer wall beyond which nothing exists. Instead, there is a receding limit, defined by what the universe has allowed to arrive. The farther that limit is approached, the less the journey resembles crossing distance, and the more it resembles reading an ancient archive whose pages grow dimmer, rather, and more difficult to separate. The boundary of the observable universe is not the final border of reality. It is the farthest shoreline of present evidence, and even as it is measured, it reminds astronomy that seeing and existing are not the same thing. The oldest light in the observable universe does not arrive as a sharp image of stars, galaxies, or any single ancient object. It arrives as a faint glow spread across the entire sky, so cold and so evenly distributed that its discovery changed the meaning of darkness itself. This glow is called the cosmic microwave background, and it marks the farthest direct layer of light that astronomy can use to study the early universe. It is not light from the first stars. It is older than that. It comes from a time before galaxies had gathered, before stellar furnaces had filled space with heavier elements, before the universe had separated into the luminous structures that now define cosmic maps. Its origin lies in a period when the universe was still hot, dense, and filled with a plasma of particles and radiation. A plasma is a gas-like state in which electrons are not yet bound into stable atoms. And in the early universe, this mattered because free electrons scattered light again and again. Photons, the particles of light, could not travel freely for long distances. They were constantly redirected, absorbed, and released inside a bright, opaque four. The universe was full of light, but that light could not yet move through space in the open way it does now. Then, as expansion continued, the universe cooled. Temperatures fell enough for electrons to join atomic nuclei and form neutral atoms, mostly hydrogen and helium. Once those electrons were bound, they stopped scattering photons so efficiently. Light was suddenly able to travel across great distances. Space became transparent. The photons released at that transition have been moving ever since, stretched by cosmic expansion from hot, visible, and infrared light into the cold microwave radiation detected today. This moment is often described as recombination. Though it was less a local event than a universal change in condition, it happened everywhere. As the young universe crossed the threshold from opaque plasma to transparent gas, the cosmic microwave background is the remnant of that change. It is sometimes called afterglow, but the word should not make it seem decorative or vague. It is a physical record, a cooled relic of the time when the universe first became visible to itself in every direction. Telescopes find this ancient radiation with a temperature only a few degrees above absolute zero. Its near uniformity is striking. No matter where instruments point, the glow is almost the same. That sameness tells a profound story. It shows that the early observable universe was remarkably smooth on large scales, with matter and radiation spread in a way that did not vary wildly from one direction to another. Yet the word almost is the key. The glow is not perfectly uniform. Tiny differences appear in its temperature. Variations so small that they require careful instruments to measure. But those faint differences are among the most important clues in all of cosmology. They reveal the seeds of later structure. Regions that were slightly denser than average could draw in more matter through gravity. Over time, those small differences grew into the beginnings of cosmic architecture. Gas gathered. Dark matter shaped deeper wells. The first stars formed. Galaxies assembled. Clusters and filaments emerged. The great unevenness of the modern universe began from slight unevenness in that ancient glow. This gives the cosmic microwave background a quiet dual nature. It looks smooth enough to suggest simplicity. Yet within its tiny fluctuations lies the origin of nearly every large structure visible today. The oldest light is therefore not only a background, it is a map of beginnings. Missions designed to measure it have turned the whole sky into a scientific surface. Not a surface in space, but a surface in time. Instruments such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory measured the glow with increasing precision, revealing its pattern of warmer and cooler patches. These patches are not stars or galaxies. They are slight temperature differences from the early universe, imprinted before ordinary matter had gathered into the forms seen now. Their scale, distribution, and strength allow cosmologists to estimate the age, composition, geometry, and expansion history of the universe. From such quiet radiation come some of the strongest numbers in modern cosmology. The balance between ordinary matter, dark matter, and dark energy, the age of the universe, the degree to which space appears close to flat on large scales. In this way, a cold microwave glow becomes a ruler, a fossil, and a boundary all at once. It is a ruler because its patterns can be compared with models of cosmic sound waves in the early plasma. These waves were not sound in air, but pressure waves moving through the dense mixture of matter and radiation before transparency. Dense regions attracted matter inward, while radiation pressure pushed outward, creating oscillations that left a preferred scale in the pattern of the background. That same scale later appears in the distribution of galaxies, linking the ancient plasma to the modern cosmic web. It is a fossil because it preserves conditions from a time long before stars could record history in their light. And it is a boundary because, before this radiation was released, the universe was opaque to ordinary light. No telescope using electromagnetic radiation can look directly past that glowing surface into earlier times. The limit is not distance alone. It is opacity. Before transparency, photons were trapped in the plasma, and their paths were scrambled too thoroughly to preserve a clear view. The cosmic microwave background is therefore like a curtain, but not one hiding an empty stage. Behind it lies an earlier universe that must be studied indirectly through theory, particle physics, gravitational effects, and perhaps one day through relic signals other than light. This is where the journey reaches a different kind of horizon. The observable universe has a light horizon, but the cosmic microwave background is an observational horizon within it. The oldest direct picture made of photons. It does not show the Big Bang itself. It shows the universe after it had already expanded and cooled for hundreds of thousands of years. The beginning lies earlier, beyond the reach of ordinary light, and any statement about it must be made with greater caution. Inflation, a proposed extremely rapid early expansion, is one way scientists explain the smoothness and geometry of the universe, as well as the origin of tiny fluctuations. But inflation is not seen as a direct photograph. It is inferred from patterns, consistency, and the way models match evidence. The cosmic microwave background is central to that testing, because it holds the imprint of conditions that may have been shaped by processes far earlier than the light itself. This makes the glow both ancient and not ancient enough. It is the oldest light available, yet it still arrives after the earliest mysteries have already passed behind the opaque wall of the young cosmos. Its silence is therefore not empty. It is disciplined. It offers evidence, but not everything. It tells where structure began to grow, but not with final certainty why the first fluctuations had exactly their observed form. It confirms a hot, dense early universe, but it leaves deeper questions about the first moments open. Even its uniformity carries a question. Regions of the early sky that appear to share nearly the same temperature were, under simple expansion alone, too far apart to have exchanged light or heat signals before the background was released. This is known as the horizon problem, and it is one reason inflation became such an influential idea. A very early burst of rapid expansion could allow regions once close enough to equalize their temperatures to be stretched far apart, producing the smoothness now observed. The evidence does not turn the earliest universe into a settled story, but it gives the story firm edges. It narrows what can be claimed. It filters speculation through the shape of the ancient sky. The glow also contains a lesson about scale. The cosmic microwave background is everywhere, passing through galaxies, planets, instruments, and bodies with almost no interaction. It is not something located in one distant direction. Each observer in the universe, if equipped with the right instruments, would see a similar background surrounding them, because each is looking back toward the time when light first traveled freely from their own observable region. This means the ancient glow is not a shell centered on Earth in any physical sense. It appears centered on every observer, because observation itself defines the visible sphere. The universe has no known central point from which this light expands outward like fragments from an explosion. Expansion happens through space, not from one privileged location within it. The background surrounds the observer because the past surrounds the observer in every direction. That is a subtle but important calm. It removes the need for a cosmic edge nearby, while deepening the sense of being embedded inside history. To look at the microwave background is not to look outward toward a wall. It is to look backward toward a time when all directions were filled with the same early fire, now cooled into a whisper. As the journey beyond the Milky Way passes through galaxy groups, distant quasars, and the limits of the observable universe, this glow becomes the oldest common reference beneath them all. Every galaxy formed after it. Every black hole grew in a universe already marked by its fluctuations. Every star, planet, and possible living world belongs to the long aftermath of that first transparent light. The cosmic microwave background does not answer every question about the beginning, but it changes the darkness into evidence. It shows that the deep sky is not merely a void filled with scattered objects. It is a layered record. And at the deepest visible layer, before any star has appeared, the universe leaves behind a nearly uniform glow with tiny imperfections large enough to become everything. A pulsar begins with a star that has already passed through its visible life. The original star burns through its fuel, loses the balance between outward pressure and inward gravity, and collapses into a remnant so compact that ordinary ideas of matter become difficult to carry any farther. What remains is a neutron star, an object with more mass than the sun compressed into a sphere only about the size of a city. It is not large in space, yet its density, magnetic field, and rotation make it one of the most precise natural machines known in astronomy. A spoonful of its matter, if such a thing could be separated and held, would weigh like a mountain. Its gravity bends the space around it. Its crust is thin, rigid, and strained. Its interior is made from matter pressed beyond the familiar form of atoms, where electrons and protons have been forced together until neutrons dominate. A pulsar is one particular face of such a remnant. It is a neutron star whose radiation beams sweep through space as the star rotates. And when one of those beams crosses Earth, telescopes receive a pulse. The pulse is not usually the star turning on and off. It is more like a lighthouse effect, though the comparison is only a beginning. The beam is tied to the star's magnetic field, and the magnetic poles do not always align with the rotation axis. As the star spins, the beams trace circles through space. If Earth lies in the path, the signal arrives again and again, with a rhythm that can be astonishingly stable. This regularity was so unexpected when pulsars were first detected that for a short time, the possibility of artificial signals was taken seriously enough to be handled with caution. In 1967, Jocelyn Bell Burnell, then a graduate student at Cambridge, noticed repeated radio pulses in data from a new telescope built to study distant radio sources. The signals were too regular to ignore and too strange to classify easily. The early nickname Little Green Men captured the nervous humor of the moment, but it also revealed the real difficulty. Nature was producing a clock with a precision that seemed almost engineered. The artificial explanation did not survive further evidence. Other similar sources were found, and the pattern began to point toward a new class of object rather than a distant civilization. The solution was more powerful than the speculation it replaced. A collapsed star, spinning rapidly and sending beams of radiation across space, could explain the pulses without requiring a transmitter built by intelligence. In that shift, the mystery did not become smaller. It became physical. The signal that had seemed almost like a message became evidence of matter under conditions no laboratory could reproduce. Pulsars soon became a way of studying the extreme aftermath of stellar death. They also became tools, because their timing can be measured with extraordinary accuracy. Some rotate slowly, sending pulses separated by seconds. Others spin many times in a single second, their signals arriving with the steadiness of a cosmic metronome. The fastest belong to a special group called millisecond pulsars. These are often old neutron stars that have been spun up by material falling from a companion star. In a binary system, gas can stream from one star toward the neutron star, forming an accretion disk. As that material spirals inward, it carries angular momentum, gradually increasing the neutron star's rotation rate. A remnant that had been slowing for ages can be given a new, rapid spin, turning into a recycled pulsar. The phrase is quiet, but the process is violent and delicate at the same time. Gas torn from a companion star heats, glows, and falls inward under intense gravity. Magnetic fields channel some of the material. Radiation changes as the system shifts between states. In some transitional pulsars, the object can appear at one time as an accreting source of X-rays and at another as a radio pulsar, depending on how much material is flowing and how the magnetosphere responds. This makes pulsars not only clocks, but laboratories of changing balance. Rotation, magnetic field, inflowing gas, and radiation compete around a body only a few dozen kilometers across. The outward simplicity of the pulses hides a complex environment where charged particles are accelerated close to the speed of light. The beams themselves arise from the magnetosphere, the region dominated by the neutron star's magnetic field. In that region, particles do not drift calmly. They are torn into ordered motion, accelerated, and made to radiate. The result can appear in radio waves, visible light, X-rays, or gamma rays, depending on the object and its state. Some pulsars are best known through radio pulses. Others reveal themselves through high-energy radiation. Some are linked to supernova remnants, where the explosion that formed the neutron star has left behind an expanding cloud of gas. The Crab pulsar is the classic example, sitting inside the remains of a supernova recorded by skywatchers almost 1,000 years ago. At its center, the neutron star spins and powers the surrounding nebula, injecting energy into a cloud that still glows from the aftermath of stellar collapse. In Zuck systems, the pulsar is not isolated from its history. The explosion remains around it, and the remnant continues to show how a dying star can seed space with new elements while leaving behind a compact engine of radiation. This connection between death and continued activity gives neutron stars their quiet importance. They are endings that keep working. A massive star dies, but the remnant can emit pulses for millions of years, slowing gradually as rotational energy is carried away. The timing of that slowdown is itself information. By measuring the rate at which pulses change, astronomers can estimate magnetic field strength, age, energy loss, and the structure of the system. Tiny deviations from perfect timing can reveal the presence of companions, changes in the star's interior, or even disturbances in space-time. Pulsars have been used to test gravity, especially in binary systems where two compact objects orbit each other. As they move, they can lose energy through gravitational waves, causing their orbit to shrink by a small but measurable amount. Long before gravitational waves were directly detected by instruments on Earth, the timing of binary pulsars provided strong evidence that such waves were real. This is one of the most elegant aspects of pulsar science. A signal arriving from a distant collapsed star becomes precise enough to measure the invisible loss of orbital energy. The pulse, repeated again and again, turns deep space into a timing experiment. Some networks of millisecond pulsars are now used in an even broader way, as a kind of galaxy-sized detector. If gravitational waves from pairs of supermassive black holes pass through the region between Earth and those pulsars, they may slightly alter the arrival times of the pulses. The effect is extremely small, but with enough pulsars watched over enough years, a pattern can emerge. The regular clocks scattered through the Milky Way become a quiet array for sensing ripples across space-time. The same kind of object that once raised the possibility of alien signals now helps search for the low, patient background of merging black holes across the universe. Yet pulsars also keep their own unresolved questions. The exact physics of their emission is still difficult. The interior of neutron stars remains uncertain because matter at such densities may behave in ways that current models can only partly describe. The boundary between a heavy neutron star and a black hole is especially important because it reveals how much pressure dense matter can provide before collapse becomes unavoidable. Each new mass measurement, each binary merger, each pulse profile adds a constraint. Pulsars are therefore not finished explanations. They are precise messengers from a regime where precision and uncertainty coexist. Their rhythms are steady, but the matter producing them remains strange. Their beams can be timed to fractions of a second, yet the deep structure of the star sending them is still hidden beneath gravity, density, and magnetic force. In the wider journey beyond the Milky Way, pulsars serve as a change of scale. After galaxies, horizon, and ancient background light, they bring attention back to compactness. The universe is not only vast because of distance, it is also vast because of intensity. A neutron star can hold stellar mass in a space smaller than many cities. It can rotate with astonishing speed. It can send signals across thousands of light years, and those signals can arrive with such order that they seem, at first, almost intentional. The silence of the sky is not empty of rhythm. It contains clocks born from collapse, beams crossing darkness, and remnants that continue to mark time long after their parent stars have disappeared. A pulsar does not speak in language, but in repetition. Each pulse is a small arrival from an extreme place, a reminder that beyond the gentle light of ordinary stars, matter can be compressed into forms that keep time with a calm severity no human mechanism has ever surpassed. TRAPPIST-1 is not bright enough to dominate a sky, and that is part of what makes its planets so revealing. It is a small red dwarf, cool, faint, and long-lived, with a mass only a small fraction of the Sun's and a glow shifted toward the red and infrared. Around it moves a compact system of 7 known rocky planets, all close enough to their star that their orbits would fit well inside the path of Mercury in the solar system. From a distance, the arrangement seems almost too small to hold such large questions. Yet the smallness is exactly what allows the system to be studied. Because the star is dim and modest in size, its planets block a measurable portion of its light when they pass in front of it. This transit method, simple in principle and delicate in practice, is how the system first became famous. A planet crosses the face of its star from Earth's point of view. The starlight dips by a tiny amount. The dip repeats, and from that repetition, astronomers infer the planet's orbit, and relationship to the star. Around TRAPPIST-1, the dips did not point to a single world, but to a closely packed family. The planets are often described as Earth-sized, but that phrase needs care. It does not mean they are Earth-like in all the ways that matter for life. It means their radii and masses place them in the range of rocky planets rather than gas giants. Their surfaces, atmospheres, histories, and climates may be very different from Earth's. Still, their sizes make them important, because small rocky worlds are the kind of places where questions about air, water, chemistry, and habitability can be asked with the most direct meaning. Several of the TRAPPIST-1 planets orbit in or near the region where temperatures could, under the right atmospheric conditions, allow liquid water on a surface. This region is called the habitable zone, but the phrase is not a promise. It is only a first filter, a way of marking where starlight is neither obviously too intense nor obviously too weak for surface water if the planet has a suitable atmosphere. The atmosphere is the difficult part. Without one, a rocky planet can lose heat quickly, suffer direct radiation, and fail to support stable surface liquid. With the wrong atmosphere, it can become too hot, too cold, too dry, too cloudy, or chemically hostile. The habitable zone begins the question, but it does not answer it. In the TRAPPIST-1 system, that question is sharpened by the star itself. Red dwarfs are common across the galaxy, far more common than sun-like stars, and they live for extremely long spans of time. If planets around them can remain habitable, then the number of possible living worlds in the universe may be very large. But red dwarfs are not gentle simply because they are faint. Many can be magnetically active, especially earlier in life, producing flares and high-energy radiation that may erode atmospheres or alter their chemistry. A planet close to such a star receives enough warmth only because it orbits nearby, and that closeness exposes it to stronger stellar activity. The TRAPPIST-1 planets therefore sit inside a balance that is both promising and severe. Their star is dim enough to give them compact orbits and observable transits, but its radiation history may have made atmospheric survival difficult. Their small distances from the star also make tidal locking likely, meaning the same side of a planet may always face the star while the opposite side remains turned away. Tidal locking is not automatically fatal for habitability. A thick enough atmosphere or ocean could move heat from day side to night side, softening the contrast. Without such circulation, the day side could become hot and exposed while the night side freezes into darkness. The question becomes not only whether a planet lies at the right distance, but whether it can move heat, preserve air, maintain pressure, and keep volatile substances from being stripped away. The planet's close spacing adds another layer. They tug on one another gravitationally, and those tugs slightly alter the timing of their transits. These transit timing variations allow astronomers to estimate masses and densities, turning repeated dimmings into information about interior structure. The system is like a set of small clocks whose ticks influence one another. When one planet passes in front of the star a little early or a little late, it records the pull of its neighbors. Through this timing, the planets become measurable, not as isolated points, but as a linked chain. Their orbits are arranged near resonances, meaning their periods have simple relationships that help maintain the compact architecture. This gives the system a quiet musical quality. Though the music is gravitational, not audible, each orbit is short. Each year on those planets lasts only a few Earth days. The innermost worlds circle close enough to receive intense radiation, while the outer ones receive less, with the middle planets occupying the zone of greatest astrobiological interest. Yet none can be judged by distance alone. A planet with too little atmosphere may be bare rock. A planet with too much greenhouse gas may trap excessive heat. A planet that once had water may have lost it during the star's more active youth, when high-energy radiation could split water vapor and allow hydrogen to escape into space. The oxygen left behind might then react with the surface or accumulate in ways that could confuse later searches for biological signs. This is one reason the search for life around red dwarfs requires caution, that a gas that seems suggestive in one context may have a non-living explanation in another. The same planet can look promising by size and distance, uncertain by stellar environment, and ambiguous by chemistry. That ambiguity is not a weakness in the science. It is the shape of the real problem. TRAPPIST-1 has become important because it concentrates many of the central questions of exoplanet research into one nearby system. How often do small rocky planets keep atmospheres around red dwarfs? How does stellar flaring change the surface environment? Can tidally locked worlds move heat efficiently enough to maintain moderate conditions? Are water-rich planets common, or do early losses leave them dry? What kinds of atmospheric signatures can be trusted? Modern telescopes now examine the system by measuring how starlight changes when planets pass in front of the star or slip behind it. During a transit, a little starlight may filter through a planet's atmosphere, if one is present, carrying traces of molecules that absorb particular wavelengths. During an occultation, when the planet moves behind the star, astronomers can compare the combined light before and during the disappearance to estimate the planet's own heat. These measurements are extremely difficult. The signals are faint. The star itself can be active and spotted. And the planets are small. A claim about an atmosphere must be separated from the behavior of the star, the limits of the instrument, and the noise in the data. In that careful separation, TRAPPIST-1 shows the discipline of modern astronomy. The goal is not to turn every Earth-sized planet into another Earth. It is to discover what kind of worlds nature actually makes. Some may be airless. Some may have thin atmospheres. Some may retain heavy gases. Some may be locked in climates unfamiliar to the solar system. The value of the system remains even if none of its planets is habitable, because a negative answer would still teach. It would show how harsh red dwarf environments can be for close rocky planets. It would narrow the search. It would help distinguish hopeful geometry from genuine environmental stability. If any of the planets does preserve an atmosphere, the importance would be equally strong, because it would show that small worlds can survive near faint active stars and remain geologically or climatically interesting over long periods. The system, therefore, does not need to provide life in order to matter. It matters because it tests a whole category of worlds that may be widespread across the Milky Way. This is the quiet shift TRAPPIST-1 brings to the journey beyond the galaxy's edge and through cosmic horizons. After the immensity of galaxy groups and ancient radiation, the search narrows to small planets moving around a small star, where the question of life depends on thin layers of gas, the behavior of starlight, and the chemistry of surfaces that cannot yet be seen. The scale contracts, but the meaning does not. A galaxy may contain hundreds of billions of stars, but habitability is decided locally, by pressure, heat, radiation, rock, water, and time. TRAPPIST-1 is a reminder that the universe is not only measured by its largest distances, it is also measured by the fragile conditions that might allow a surface to remain temperate under a faint red sun. The planets continue to cross their star in silence, each transit a small subtraction of light, each observation a patient attempt to learn whether any of these close, dimly lit worlds has kept an atmosphere around it. Nothing in the system has yet turned possibility into certainty, and that restraint is part of its importance. The promise of TRAPPIST-1 is not that it has answered the question of life beyond Earth. It is that it has made the question more exact, placing it around real planets with measured orbits, real starlight, and atmospheres that may or may not still be there. A magnetar is not impressive because of its size. It is impressive because almost everything about it has been forced into compression. A massive star dies. Its core collapses. And, under rare conditions, the remnant becomes a neutron star with a magnetic field so intense that magnetism is no longer a quiet property of matter, but the main architecture of the object. The star itself may span only the width of a city, yet it can contain more mass than the Sun. Pressed into a sphere where atoms have lost their ordinary separateness, in a normal star, heat, pressure, and nuclear burning define the visible life of the object. In a magnetar, that life is already over. What remains is a compact remnant whose crust, interior, and surrounding space are dominated by magnetic stress. The field is not merely strong by the standards of planets or stars. It is strong enough to distort the behavior of matter, to shape radiation, and to store enormous energy in a region smaller than many landscapes on Earth. This is why magnetars belong naturally after pulsars in the journey. Both are neutron stars. Both are born from collapse. Both can rotate and send signals across space. But a magnetar shifts the emphasis from clock-like regularity to contained strain. Its power lies less in steady repetition than in the possibility that a stressed magnetic field can rearrange itself and release energy suddenly. The surface of a neutron star is not a soft surface in any familiar sense. It is a crust of dense matter held under gravity so strong that mountains, if they exist, would be tiny by standards and still immense in meaning. Beneath that crust, matter may exist in forms that remain uncertain, arranged by pressures beyond laboratory reach. Around the star, the magnetosphere is filled with charged particles forced to follow magnetic lines. If the field twists or the crust shifts, energy can move outward in bursts of X-ray and gamma-ray radiation. These bursts can be brief, but the energy involved is extraordinary. Some magnetars are known as soft gamma repeaters because they emit repeated flashes of lower energy gamma rays. Others are called anomalous X-ray pulsars because their X-ray brightness cannot be explained simply by the loss of rotational energy, as in ordinary pulsars. These names began as observational categories, ways of describing how the objects appeared before their deeper connection was clearer. Over time, they came to be understood as related expressions of the same underlying kind of star. The magnetar is a neutron star whose magnetic field is decaying, twisting, and heating the star, producing radiation beyond what rotation alone can supply. This difference matters because it shows that a neutron star can be powered by more than one reservoir. A radio pulsar spends rotational energy as it slows, and an accreting pulsar gains energy from material falling inward. A magnetar draws from magnetic energy stored in its field. Each source leaves a different signature, and Sky contains examples that blur the boundaries between them. Some magnetars pulse. Some produce bursts. Some remain quiet for long periods and then awaken. In 2004, a giant flare from a magnetar in the Milky Way reached Earth after crossing tens of thousands of light years. The event lasted only a short time in its most intense phase. Yet it briefly altered detectors and affected the upper atmosphere. It did not endanger the planet, because the source was far away, but it revealed how much energy a magnetar can release when its magnetic structure shifts. A compact remnant, invisible to the eye and distant across the galaxy, can announce a fracture in its magnetic field strongly enough to be measured across interstellar space. The burst begins near a star, only a few dozen kilometers wide, but the signal becomes galactic. The cause is still studied through models. One possibility is that the magnetic field inside the neutron star evolves and stresses the crust until it cracks or yields. Another is that the outer magnetic field becomes twisted and then reconnects, changing its arrangement and releasing stored energy. These processes may work together, because in a magnetar, the crust and magnetic field are not separate actors. The field threads the star, shapes the plasma around it, and stores tension that can be transferred into heat and radiation. A starquake is one way to describe the crustal failure, but even that term only points toward the idea. There is no ordinary ground there, no familiar fault line, no slow motion of plates. There is dense matter under crushing gravity, responding to magnetic stress. The result can be a flare whose first spike is followed by a fading tail, sometimes modulated by the star's rotation. In that fading tail, the neutron star reveals itself again as a rotating body, turning through its own aftermath. Magnetars also teach through their rarity. Only a small number are known compared with the many ordinary stars in the galaxy. And even among neutron stars, they represent a special path. Their active magnetar phase may be relatively brief on cosmic timescales before the strongest field decays and the object becomes quieter. This short visible life makes them harder to find and more valuable when discovered. They are not simply exotic curiosities. They may help explain fast and powerful transients, the brief flashes and bursts that appear across the high-energy sky. Some theories connect magnetars to certain supernovae, gamma-ray bursts, or fast radio bursts, depending on the conditions of their birth and magnetic evolution. Not every such event requires a magnetar, and the evidence must be weighed carefully. But the possibility keeps returning because magnetars hold so much energy in such little space. A newborn magnetar, spinning rapidly after a stellar explosion, could inject energy into the expanding debris around it, making some supernovae unusually bright. These ideas do not reduce the mystery. They give it a physical candidate. They place the unknown inside a known class of extreme remnants rather than leaving it unanchored. The closest magnetars are safely distant, and most are studied not as visual objects, but through X-ray, gamma-ray, infrared, or radio observations. Their small size makes direct imaging impossible with ordinary means. What astronomers collect instead are pulses, spectra, bursts, fading light curves, and changes in timing. From those signals, the invisible structure is inferred. A magnetar cannot be approached, sampled, or seen as a disk. It must be understood through the way it disturbs the space around it and releases energy into it. Even its magnetic field is measured through consequences such as the slowing of rotation, the shape of radiation, the heating of the surface, and the timing of bursts. This gives the object a strange observational character. The central star remains almost hidden, while its field writes the evidence. Near the center of the Milky Way, a magnetar has been found close on the sky to the region of Sagittarius A, the supermassive black hole at the galactic center. Its presence there is valuable because it offers a rare probe of the environment around the center, where gravity, gas, magnetic fields, and stellar remnants crowd together. The magnetar's pulses can carry information about material along the line of sight, helping astronomers study the turbulent region between Earth and the galactic core. Again, the magnetar becomes more than an object. It becomes an instrument provided by nature, a compact beacon shining through a difficult part of the galaxy. Yet even with such uses, the inner nature of magnetars remains unsettled. Their fields may be tangled and multipolar, more complex than a simple bar magnet shape. Their interiors may contain superconducting or superfluid matter, terms that describe states where particles move with unusual collective behavior. Their crusts may fail in ways that are only partly understood. The boundary between a magnetar, a high-field pulsar, and a quieter neutron star may not be perfectly sharp. It may be an evolutionary sequence, a range of magnetic histories rather than separate boxes. This uncertainty is not a flaw. It is the point at which evidence still meets matter under conditions almost beyond imagination. After pulsars introduced the idea of stellar remnants as clocks, magnetars reveal the same family of objects as reservoirs of stress. They show that the universe can hide immense force, not only in enormous structures like galaxies and black holes, but in compact stars, whose smallness makes the intensity stronger. A magnetar is a reminder that scale in astronomy has two directions. There is the outward vastness of intergalactic distance, and there is the inward vastness of density, field strength, and pressure. Both belong to the same cosmos. In the quiet dark between stars, a magnetar may sit unseen for years, slowly losing rotational energy, its magnetic field evolving beneath and above the crust. Then a shift occurs, and a pulse of high-energy light crosses the galaxy, carrying news of a surface and field that no eye could survive nearby and no instrument can touch directly. The object returns to quiet. But the quiet is not emptiness. It is stored tension, fading heat, and the slow decay of one of nature's strongest magnetic fields. The journey beyond the Milky Way will soon widen again toward quasars and black holes, where darkness becomes luminous through falling matter. Before that widening, the magnetar holds attention on a smaller truth. Some of the most powerful places in the universe are not large enough to fill a horizon, but dense enough to make space around them answer. A quasar makes darkness visible by feeding it. At the center of a distant young galaxy, a supermassive black hole may be surrounded by gas that has not yet crossed the event horizon. And it is this waiting material, not the black hole itself, that can blaze across the universe. The event horizon is the boundary beyond which light can no longer escape, so the interior remains hidden in the strictest sense. But outside that boundary, matter can be heated to extreme temperatures as it spirals inward through an accretion disk. Gas rubs against gas. Gravity converts falling motion into heat. Magnetic fields twist through the flow. Radiation pours outward from a region smaller than the galaxy around it, and the result can outshine hundreds of billions of stars. A quasar is therefore not a lamp placed beside a black hole. It is the visible consequence of matter losing its freedom just before it disappears. This is why quasars became so important once their nature was understood. At first, many looked almost star-like in telescopes, compact points of light that did not reveal the galaxies around them. Their name came from that misleading appearance, because they seemed quasi-stellar, nearly like stars, while their redshifts showed that they were far beyond the Milky Way. The implication was difficult to avoid. If such objects were truly so distant and still so bright, then their energy output had to be enormous. Ordinary stars could not explain it. A whole galaxy of ordinary stars could struggle to explain it. The central engine had to be something more compact and more efficient. And accretion onto a supermassive black hole became the explanation that turned the puzzle into a physical process. In a calm sense, the quasar is one of the universe's most precise reversals. The black hole itself is dark because escape is impossible from inside the horizon. Yet the environment around it can be among the brightest known phenomena. Darkness does not shine, but falling matter does. The more rapidly a black hole feeds, the more luminous the surrounding disk can become, up to limits set by radiation pressure, available gas, and the structure of the flow. Some quasars also launch jets, narrow streams of particles moving outward at nearly the speed of light, guided by magnetic fields and the rotation of the central system. When those jets point near Earth, the object can appear even more intense. But even without such alignment, the accretion disk alone can make a distant galaxy's nucleus dominate everything around it. TON 618 is one of the most famous examples because it places this process at an almost difficult scale. It is a quasar whose central black hole has been estimated at tens of billions of solar masses, placing it among the ultra-massive black holes known to astronomy. The exact mass remains a matter of measurement and interpretation, because no one weighs such an object directly. Astronomers infer it from the width of emission lines, the brightness of the active nucleus, the motion of gas, and models of how material behaves near the central engine. Even with uncertainty, the conclusion remains imposing. The black hole in TON 618 is not merely a larger version of the one at the center of the Milky Way. It belongs to a scale where the event horizon could swallow the solar system many times over, and where the feeding region can radiate with the power of an entire cosmic metropolis compressed into one nucleus. Yet the quasar is so far away that its light has crossed most of cosmic history before arriving. Observing it is not seeing a present neighbor. It is receiving an old message from an earlier universe. When active galactic nuclei were more common and many massive black holes were still growing rapidly, that time difference matters because the largest black holes raise a formation problem. A stellar mass black hole can form when a massive star collapses. A supermassive black hole can then grow by feeding on gas and merging with other black holes. But the most massive examples, especially those seen when the universe was young, place pressure on simple timelines. How did they become so large so early? Did they begin from the deaths of the first massive stars? Did some form from the direct collapse of enormous gas clouds? Did mergers build them quickly inside dense young galaxies? Did early accretion proceed faster than later conditions would normally allow? The evidence does not point to only one pathway. It suggests that nature may have used several. A black hole can grow when gas loses angular momentum and falls inward. It can grow when galaxies merge and their central black holes eventually find each other. It can grow in dense environments where fresh material continues to arrive. But growth is limited by feedback. As the accretion disk shines, radiation pushes on the surrounding gas. Jets and winds can heat or expel material. The same feeding that lights the quasar can reduce the fuel supply. This makes the largest black holes not only objects of size, but records of balance. They reveal how gravity gathers matter and how radiation resists that gathering. In some galaxies, the active nucleus may regulate star formation by heating gas that otherwise might cool into new stars. In others, it may help drive outflows that change the future of the galaxy. A black hole, though small compared with the full stellar body of its host, can influence the evolution of regions far larger than itself. This connection is visible in the relationship between supermassive black holes and the central bulges of galaxies. The masses of central black holes tend to correlate with properties of their host galaxies, suggesting that they do not grow in complete isolation. Galaxy and black hole shape each other over long intervals, not as equals in size, but as linked parts of one gravitational and energetic system. Nearer examples make this relationship easier to study. Sagittarius A at the center of the Milky Way is quiet compared with a quasar, feeding only weakly in the present era. Yet, its mass and position reveal that even a calm spiral galaxy can contain a central black hole of millions of solar masses. The black hole in the galaxy, Messier 87, is far more massive and was the first to be imaged through the shadow cast against its surrounding emission. That image did not show the event horizon as a surface. It showed the dark central region created by light paths bending in strong gravity. Surrounded by hot material close to the black hole, it turned a mathematical boundary into an observed structure. Not by seeing inside the darkness, but by seeing what the darkness prevented from arriving. Objects like TON 618 push that same idea outward to a scale where direct imaging is not yet possible. Their black holes are studied by inference from light produced near them, and the inference is powerful but indirect. The brighter the quasar, the more difficult it can be to see the host galaxy, because the nucleus overwhelms the surrounding starlight. The object that reveals the black hole also hides the environment that helps explain it. This is one of the recurring patterns in astronomy. The strongest signal can obscure the quieter context. To understand a quasar, astronomers must separate nuclear light from galactic light, broad emission from narrow emission, accretion physics from cosmic distance. Each separation adds caution. A mass estimate becomes a range. A brightness becomes a clue rather than a final answer. A black hole becomes known through the motion and radiation of everything that has not yet fallen it. Ultra-massive black holes also deepen the question of what happens when galaxies merge. When two large galaxies combine, their central black holes may sink toward the merged center through interactions with stars and gas. Eventually, they may form a binary and spiral inward, releasing gravitational waves as they approach coalescence. The most massive pairs would produce low-frequency waves, too slow for detectors built for stellar mass black hole mergers, but potentially detectable through the timing of pulsars across the galaxy. In this way, the earlier section's clocks return in a new role. Pulsars may help reveal the distant merging of the largest black holes, linking compact neutron stars to the heaviest dark objects in galactic centers. The universe connects its extremes quietly. A millisecond pulse in the Milky Way may carry a slight timing shift from a pair of supermassive black holes far beyond direct sight. The black holes themselves may have grown during ages when quasars were brighter and galaxies more gas-rich. Their mergers may continue to shape the background hum of space-time. What begins as falling gas around a horizon expands into a story of galaxy formation, feedback, cosmic history, and gravitational waves. The strange calm of a black hole is that it can be both hidden and central. It gives off no light from within, yet it can organize the brightest engines in the universe. It occupies a region tiny compared with a galaxy, yet it can influence gas across thousands of light years. It is defined by absence, yet discovered through consequences. Quasars make those consequences visible from distances so great that they become markers of the early cosmic web. TON 618 stands not simply as a champion of mass or luminosity, but as a reminder that the most luminous beacons may be powered by the approach to disappearance, matter circles, heats, shines, and then passes beyond recovery. The light travels on, crossing billions of years, arriving long after the act of feeding that produced it. In that delayed glow, the universe shows a quiet paradox. Some of its brightest signals are written at the edge of places from which no signal can ever return. The silence around other minds begins not with emptiness, but with abundance. The Milky Way contains hundreds of billions of stars, and many of those stars carry planets. Some planets are too hot, too cold, too massive, too airless, or too unstable for life as Earth understands it. But the number of worlds is so large that even rare possibilities begin to matter. Around faint red dwarfs, around sun-like stars, around stars older than the sun, Rocky planets may orbit in regions where warmth is not immediately impossible. Chemistry may gather. Atmospheres may persist. Oceans may form or vanish. On at least one planet, in one ordinary spiral galaxy, matter has become capable of asking about the rest. The Fermi paradox rises from the contrast between that abundance and the absence of confirmed contact. If planets are common, and if life can sometimes become intelligent, and if intelligence can sometimes build technology, then the sky might be expected to contain evidence of another civilization, not necessarily visitors in a dramatic sense, and not necessarily messages written for Earth, but some trace that technology has appeared elsewhere, a narrow radio signal, an artificial pattern of light, a probe, a large energy structure, or an atmospheric sign difficult to explain by natural processes. So far, no such evidence has been confirmed. The quiet is not proof that Earth is alone, but the state of the evidence is serious enough to require explanation. Enrico Fermi gave the paradox its most famous form in the 20th century. But the deeper question is older than one conversation. It belongs to astronomy, biology, technology, and time at once. The difficulty begins with the fact that no part of the chain is well known beyond Earth. The formation of planets is now known to be common, but the origin of life remains understood from only one example: the rise of complex cells, multicellular organisms. Intelligence, language, and technology may each require conditions that are ordinary, rare, or built from sequences of accidents that cannot yet be estimated. The Drake equation was created to organize this uncertainty, not to remove it. It asks how many stars form, how many have planets, how often life begins, how often intelligence emerges, how often detectable technology appears, and how long such signals last. Some factors are now better constrained than they once were. Others remain nearly blank. The equation is therefore less a calculator than a frame for honest ignorance. It shows where knowledge is strong and where it is still thin. The silence may come from any weak link. Life may be common but simple. Complex life may be rare. Intelligence may appear only occasionally. Technological civilizations may be brief, or they may be long-lived but difficult to notice. The first possibility is that life itself is hard to begin. Earth shows that life can arise, but it does not show how easily. The early planet offered water, rock, energy, organic chemistry, impacts, volcanic settings, minerals, and changing atmospheres. Somewhere in that restless environment, chemistry crossed into heredity and evolution. Yet the exact pathway remains unknown. If that transition is extremely unlikely, then the galaxy may be rich in habitable planets and poor in living ones. The second possibility is gentler, but still limiting microbial life may be common, while complex life is unusual. For most of Earth's history, life remained microscopic. Large animals, nervous systems, and technological minds appeared only late, after long changes in atmosphere, oceans, climate, and biology. A galaxy full of microbes would be alive, but mostly silent. It would not build transmitters, alter starlight in obvious engineered ways, or send probes between stars. A third possibility is that intelligence does not inevitably lead to detectable technology. A planet may contain complex ecosystems, perception, memory, communication, and social behavior without producing a species that studies electricity, builds radio instruments, or leaves its atmosphere. Intelligence can be useful in many forms, and only one known lineage has turned it into astronomy. Another possibility is duration. Civilizations may appear, become briefly detectable, and then fade from view. They may destroy themselves, lose technological capacity, choose low-emission systems, or move into forms of communication that do not leak strongly into space. Humanity has used radio transmissions for only a very short time, and even those signals weaken rapidly with distance. If the detectable phase of a civilization is brief compared with the age of the galaxy, then two civilizations may exist in the same galaxy and still miss each other across time. The silence would be a timing problem rather than a population problem. There may have been voices before Earth had ears, and there may be listeners long after Earth has gone quiet. Time is as large a barrier as distance. The Milky Way is more than 100,000 light-years across, and even light needs ages to cross it. A conversation between distant civilizations would be stretched beyond ordinary cultural memory. A signal sent now from one side of the galaxy could arrive after the world that sent it had changed beyond recognition. This does not make communication impossible, but it makes it slow, fragile, and dependent on persistence. Another explanation is that searches have barely begun. Radio surveys, optical searches, infrared studies, and atmospheric observations cover only a small part of the possible ways technology might appear. A civilization may use narrow beams that rarely cross Earth. It may communicate with methods not chosen for interstellar leakage. It may use energy efficiently enough to avoid producing large waste heat signatures. It may live around stars not yet examined carefully, or in regions hidden by dust. The absence of detection across a limited search space is not the same as a complete silence across all possibilities. Astronomy has often mistaken the limits of its instruments for the limits of reality, only to revise the map later. Still, the failure to find a signal after decades of searching cannot simply be ignored. It tells something about how narrow the search has been and how careful future claims must be. The zoo hypothesis offers another kind of answer. Advanced civilizations might know of Earth and choose not to interfere. It is a difficult idea because it can explain almost any silence and is therefore hard to test. A good scientific explanation must risk being wrong. Still, the idea reflects uncertainty about behavior. Technology does not reveal motives. A civilization old enough to cross interstellar distances may not behave in ways familiar to a young technological species. It might avoid contact, value quiet observation, or have no interest in biological worlds at all. The problem is that such possibilities quickly become speculative. The more grounded explanations return to detectability, rarity, and time. A related idea is the great filter, the possibility that some step between lifeless chemistry and long-lived galactic civilization is extremely difficult. The filter may lie behind Earth, in the origin of life or the rise of complex organisms. If so, humanity may be rare because earlier steps were rare, or the filter may lie ahead, in the dangers that technological species face once they gain great power over their environments. A species capable of changing a planet may also be capable of destabilizing the conditions that support it. The Fermi paradox therefore turns outward and inward at the same time. It asks about alien life, but it also asks how long any technological species can remain wise enough to be detectable. The search continues because the silence is not a conclusion. It is a measurement waiting to be improved. New telescopes can examine exoplanet atmospheres for gases shaped by biology or industry. Radio arrays can survey more stars with greater sensitivity. Infrared observations can look for unusual waste heat. Studies of nearby planetary systems can identify stable, temperate worlds that deserve deeper attention. At the same time, The standards for evidence must remain high. A strange signal is not enough. It must repeat, localize, resist natural explanations, and survive independent scrutiny. A possible biosignature in an atmosphere is not enough by itself. It must be understood in the context of the planet, the star, the chemistry, and the false positives nature can produce. The same restraint that makes discovery slower makes it trustworthy. In the calmest form, the Fermi paradox is not a demand that the universe answer quickly. It is a recognition that the sky contains a tension between scale and evidence. There are many stars, many planets, many chances, and yet no confirmed neighboring mind. That tension may one day break with a signal, a spectrum, a probe, or an unmistakable planetary atmosphere. It may also persist for centuries, narrowing slowly as searches deepen. Either outcome would teach. A detection would show that intelligence is not confined to one world. Continued silence would sharpen the question of rarity and survival. For now, the Milky Way remains rich in possible homes and poor in confirmed company. Its stars shine without explanation from anyone else. Its radio sky murmurs with natural sources, pulsars, magnetars, gas clouds, and active galaxies, but not yet with a verified technology beyond Earth. After the journey through companions, horizon, ancient light, neutron stars, exoplanets, and black holes, the silence does not feel empty. It feels structured by unanswered conditions. It may be the silence of distance, the silence of rarity, the silence of timing, or the silence of civilizations that do not reveal themselves in ways currently understood. The unanswered sky remains open, not because anything can be claimed inside it, but because the evidence has not yet closed the question. The return home begins without reversing the journey. After the local group, the observable horizon, the oldest light, the collapsed stars, the compact planetary systems, the magnetars, the quasars, and the silence around other minds. The Milky Way is no longer only the pale band that crosses a dark rural sky. It has become a position inside many scales at once. It is a spiral galaxy with arms, dust, gas, old stars, young stars, a central black hole, a wide halo, and a hidden dark matter framework. It is also a member of a small galactic family, a future partner in a merger with Andromeda, a point inside the larger cosmic web, and one temporary vantage from which the universe can measure itself. This is one of the quiet transformations of a journey beyond the galaxy. The farther the view travels, the less home disappears. Instead, home gains context. The sun becomes one star among the many in the disk. The disk becomes one luminous structure inside a larger halo. The halo becomes part of a local group shaped by past captures and future mergers. The local group becomes one bound island within an expanding universe where more distant galaxies slowly recede from communication. The observable universe becomes not the whole of existence, but the region whose light has reached the present moment. At each widening scale, the familiar is not erased. It is placed more carefully. The Milky Way's stars still matter, but now they shine inside a history that began before stars existed at all. In the faint fluctuations of the cosmic microwave background, the planets still matter, but now they belong to a galaxy where small, rocky worlds may be common and where the conditions for life remain difficult to judge from afar. The question of intelligence still matters, but now it sits among uncertainties of biology, timing, survival, and detection. The map has grown, and the growing map has made every certainty more exact and every uncertainty more honest. What seemed at first like a journey toward a boundary has become a lesson in changing kinds of edges. The Milky Way has no clean rim, only a thinning of stars and a continuing reach of gravity. The local group has no wall, only a range where shared attraction yields gradually to larger cosmic motion. The observable universe has no visible shell at its far side, only a horizon of information shaped by the age of the cosmos and the expansion of space. Even the cosmic microwave background, the oldest direct light available, is not the beginning itself, but the moment when the universe became transparent enough for light to travel freely. Every edge turns into a threshold. Every threshold reveals another condition beneath it. The same pattern appears on smaller scales. A pulsar looks like a simple repeating signal until it becomes a neutron star with a hidden interior and a beam shaped by magnetism. A magnetar looks like a compact remnant until its field reveals stored energy and sudden release. A quasar looks like a bright point until its redshift and luminosity reveal an active galaxy powered by matter near a black hole. TRAPPIST-1 looks like a faint red star until repeated dimmings uncover a chain of rocky planets whose atmospheres remain uncertain. The universe repeatedly refuses the first impression, not by becoming more theatrical, but by becoming more layered. This is why the calm study of space can hold attention without noise. The evidence itself carries the motion. A small pulse becomes a collapsed star. A faint glow becomes the early universe. A pale smudge becomes Andromeda. A missing signal becomes the Fermi paradox. A dark center becomes a luminous accretion disk. The journey outward, therefore, returns with a different understanding of darkness. Darkness is not a single absence. Between the stars, it may hold gas too thin to glow brightly. Around galaxies, it may carry dark matter whose gravity shapes visible motion. Beyond the reach of present observation, it may contain regions whose light has not arrived or may never arrive. Around a black hole, darkness marks a boundary from which light cannot escape, while just outside it, matter can burn with extraordinary power. In the night sky, darkness is also the background against which every measurement is made. It is not empty by default. It is simply not yet fully translated into evidence. This distinction matters for the quietest part of the journey, the part concerning life. The absence of a confirmed signal from another civilization does not prove that Earth is unique in every way. It also does not permit easy certainty that the galaxy is crowded with minds. The silence remains disciplined by evidence. What can be said is narrower, and more meaningful planets are common. Chemistry is widespread. Water appears in many cosmic settings. Organic molecules form in space and on worlds. And life has arisen at least once. Beyond that, the path from chemistry to cells, from cells to intelligence, and from intelligence to detectable technology remains largely unmeasured. In this uncertainty, Earth is not diminished. It becomes rarer in a practical sense, because it is the one place where the full chain is known to have happened. The planet is small against the galaxy, but it is not small in significance. It is the current site of awareness in the known story, the place from which the Milky Way has learned to map itself from within. The return to home, then, is not sentimental. It is structural, a world capable of studying the cosmic microwave background, timing pulsars, measuring exoplanet transits, imaging the shadow of a black hole, and detecting gravitational waves is part of the universe becoming legible to itself in one location. That does not make the location central in space. It makes it important in meaning. The evidence gathered from beyond the Milky Way comes back to Earth as a set of limits and permissions. It permits the statement that galaxies grow by merging, that space expands, that the early universe was hot and dense, that collapsed stars can become precise clocks or magnetic reservoirs, that rocky planets exist around other stars, and that black holes can power the brightest known galactic nuclei. It limits claims about what lies beyond the observable horizon, about life on distant planets, about the interiors of neutron stars, about the first moments of the universe, and about the presence of other technological beings. A mature map contains both kinds of knowledge. It knows where its lines are firm and where its blank regions remain. The old image of a universe with a reachable border gives way to something quieter and more durable, a universe made of nested horizons. Some horizons are practical, set by instruments. Some are physical, set by light speed, opacity, and expansion. Some are conceptual, set by theories not yet complete. Some are biological, set by the difficulty of recognizing life from a distance. The journey beyond the Milky Way passes through all of them, and none has to become a final wall in order to matter. A horizon can guide inquiry even when it cannot be crossed. It can show where knowledge ends for now, and where the next form of patience begins. From this perspective, the Milky Way is both shelter and subject. It holds the sun in one of its arms, but it also hides parts of itself behind dust. It supplies pulsars as clocks, star-forming regions as laboratories, old halo stars as fossils, and neighboring dwarfs as evidence of growth. It gives a foreground through which the farther universe must be seen, and a home ground from which the farther universe can be understood. Beyond it lie Andromeda, the local group, the cosmic web, distant quasars, early galaxies, and the ancient microwave glow. Within it lie the instruments, minds, and fragile planet that gather those signals. The two directions cannot be fully separated. To look outward is also to learn what kind of place is doing the looking. The quiet journey ends not at an edge, but at a clearer orientation. The universe remains larger than the observable part. The Milky Way remains unfinished. The future merger with Andromeda remains far ahead. The oldest light remains a boundary to direct vision. The strange stars continue to pulse, flare, and cool. The black holes continue to feed or sleep. The small planets around faint stars continue to cross their suns in tiny dips of light. The silence around other minds remains open. None of these facts closes the map. Together, they make it steadier. Home is not outside the mystery, and the mystery is not outside home. The galaxy that carries the sun is one quiet structure among many, drifting through a universe where every answered question leaves a more precise darkness around it, and where the calm work of understanding continues from one small world beneath one ordinary star. The journey settles where it began, inside a galaxy that is neither the center of the universe nor a small thing in any simple sense. The Milky Way remains wide enough to hold billions of quiet histories, yet it is also only one structure among many, shaped by companions, drawn toward Andromeda, surrounded by horizons that belong to light, time, and knowledge. Beyond it, the universe does not offer a final wall. It offers layers. Some are bright with galaxies, some are dim with ancient radiation, some are hidden by distance, expansion, or the limits of present instruments. The calmest lesson is not that the map is incomplete, though it is. It is that incompleteness can have form. A pulsar gives rhythm to the dark. A magnetar stores force in a narrow remnant. A quasar shines from the edge of disappearance. A red dwarf carries small planets through faint light. A silent sky leaves room for caution, patience, and a deeper kind of wonder. Every signal that reaches Earth has traveled through conditions that no single life could cross, and yet the signals arrive stretched, weakened, delayed, but still carrying structure. The universe becomes understandable not all at once, but in traces, and the traces are enough to make the darkness less empty. The Milky Way continues to turn. Its companions continue their slow passages. The oldest light continues to fill the sky in every direction. Far beyond sight, more regions may exist without ever becoming part of any present observation. Within sight, there is already more than enough to study gently for ages. The quiet journey does not close with certainty. It closes with orientation, with a small world held inside a spiral galaxy, listening patiently to an immense and unfinished night.